Let's take a look. So here is the Iris machine learning code. I'm going to take you through this really quickly. This first part, you can see I'm importing all kinds of crap. That's all you need to know about it. Pandas, there's a math plot library. sklearn is my machine learning tool set. So I'm importing data sets, model selection, metrics. There's not enough time. In our data science program, we have a whole class on just machine learning. So I'm giving you in a few minutes a preview of something that's really complex. In order to train the puppy, you've got to know some things. But these are all sklearn is always, that's all machine learning stuff. And then you can see I'm getting an iris data set and I'm creating it to a data frame. So I'm using pandas here, creating a data frame that has those data frames. So those pandas data frames we're using for analysis later on. It's going to print the head of the data frame and a description of the data. So let's take a look at that before I do anything else. Let's run that. Okay, so here is, like I said, sepal length, sepal width, petal width, species. So that's the test data. Here are the descriptive statistics. These don't really mean a whole lot to us because we're not flower experts. But the count, the mean, standard deviation. The count is probably the most important thing. We've got 150 records here. That's relatively small for training a machine learning model, but it allows us to use that effectively. So let's uncomment the rest of this so that I can show you what it does here. Let's pull this into our notebook here and see what we can do. Let's get rid of all that, and we'll start here. Okay, so I'll finish previewing the rest of this. We've got the data frame, we're showing the basic statistics, and these lines of code here are what give us our machine learning. So the first thing we're going to do is we're going to split the data into training data and test data. The training data is what we use to train the puppy. The test data is what we use to see whether we trained the puppy well enough or not. So what we're doing is we're splitting it into X and Y test sets, because what we have to do is predict one based on the other. So we're using X is our whole matrix that says here is all of the measurements for each flower. So each flower has 4 measurements. That's what X is. Y is the category of flower. It is the flower subspecies name. So setosa or the other things. Test size says what proportion or what percentage of that data are we going to use for the test. And then the rest of it we use for the training. So the first 30% randomly chosen, and 42 is just a number that we use to make sure that the randomness happens the same each time. But we're randomly picking 30% of that data, and we're using the 30% to train the puppy. So 30% of 150, about 50. Okay, so about 50 records we're using to train the puppy. And then we're using the other 100 to see how we did. That's all that means. And then we're using a logistic regression model. That is a specific mathematical model that we're using to train the machine. There are lots and lots of models, but a logistic regression basically says, let's see if the sepal length and the petal length are related to the flower type, which we kind of know they are. So we would know that by looking at the data and doing basic statistics. That would tell us what model do we want to use. Max iteration says how much time do we want to spend doing this. The higher the number is, the more we train the puppy. And this says, okay, let's do this. The model is going to use the training data for these two models. So it's going to say, we're going to train you how to predict this, or how to predict this based on what's in this. And then finally, we come up with a Y prediction based on the X test. What that says is, how do we predict Y based on X after we've trained it? And then we're generating something called a confusion matrix, which is that table that I just showed you with the diagonal numbers that look a certain way. And then finally, we'll print a classification report, which kind of shows you another view of the data. So let's run this. Let's run it in the notebook here and see how it does. Okay, so here is our stuff. These are the headings. This is the head of the data frame here. These are the descriptive statistics that we talked about before. And then we've got more descriptive statistics with petal width included. Here is the confusion matrix. I know it doesn't seem all that grand when we print it out, but you can see it's got the same numbers that I just showed you in the table, where we've got 40, 30, and 31 with an error of 4 cases that were misidentified. And remember, that is using 30% of the data to train, 70% to test. If we want to get more accurate, then what we would do is give it more, we would give it more data to train. So let's go back up. Here, I'll just use this one. This is the tinkering that we are allowed to do. So if I want to use more data to train it and less to test it, I would just give it a higher proportion or a lower proportion of test size. So let's go half and half. Half to train, half to test. Now remember, our confusion matrix looked like this before. Let's keep what's there actually. So let's keep that at 7. And then I'm going to retrain and regenerate that model in a new cell. So remember, it keeps everything that was there before. So that's with 7. Let's change it to 5. Okay, now look. Out of the test cases that it chose, it's got 29, 23, and 23 correctly identified, and all zeros everywhere else. Now, the number of test cases went down. Why? Because I shifted some of that data into the other category, into the training category. So we have, what, 75 test cases, which should be right because we had 75, half and half. We got 150, so half of that is 75. So I can start tinkering with this. At 0.5, it makes 0 errors. At 0.6, okay, so this is where we have 2 errors. So at about 0.5, at 0.55, it's still making 0 errors. So I can find out how much training it actually needs in order to get a perfect score. And you can see here, this part of the table has 1s all over the place. 1 basically means it scored 100% on the exam. Okay, so if I go back to the 7, or if I scroll up here to the 7, you can see the precision of each flower type, 0, 1, and 2. These are setosa, versicolor, and the other one, I can't remember the name of it. So it scored 100% on that one, and it correctly identified 97% of the next one and 91% of the last kind. So that's still good. It's still like an A, but you can get to a point where you've trained it good enough to get 100%. And literally, that's what machine learning is. It is learning to fine tune a training set of data. And obviously, this is a very simple example that is used for instructional purposes. And again, real world data is a lot squirrelier than this. It's a lot harder to get it straight. But this gives you an idea of what does machine learning look like? What are we getting out of this? And then what can I do with this model? Now that it's trained at 100%, I can actually take this machine, this model that I've created and trained, I could feed new data into it now. So as people go out and they measure other iris flowers, if they're like, I don't know what kind of flower this is or what subspecies this is, if you give me the measurements for a subspecies of flower, I can tell you with a lot of confidence what kind of flower that is. So it allows me using new data to predict what the species is of the flower. And again, simple example, but with huge implications of things. Okay, one of the ways that this is being used right now is, in my son's work at Microsoft, some of the stuff that he's doing is really interesting. With taking people's resume and being able to predict what kind of jobs they would be good at or what kind of training they should have, things like that. So there's really interesting stuff going on, and that's all using machine learning, but it's using machine learning and vast amounts of data. Okay, so the more data you have, the better your model can be.